50 years after Apollo, we are going back to the moon. But this time, the plan is not a sprint for a flag and a photograph. The goal is to arrive, work, and stay. That change makes everything harder. The moon looks calm in slow shots from orbit. It is a harsh, airless rock. There is no atmosphere to slow a spacecraft. There is no global magnetic shield to soften radiation from the sun or deep space. Dust acts like powdered glass. Craters and boulder fields run to every horizon. Days last 2 Earth weeks, and nights last 2 Earth weeks. Artemis is the plan to handle that reality. Picture a step-by-step bridge from Earth to the lunar surface and back, built with reusable pieces instead of one-off stunts. A heavy rocket sends a cruise ship into deep space. The crew uses a small outpost in lunar orbit, a gateway that works like a spaceport. A human landing system ferries astronauts down to the surface and back up again. Cargo missions deliver tools, power systems, and science gear ahead of the crew. New spacesuits let astronauts bend, kneel, and work for hours without tearing seals. Why is returning hard? Because sustainable exploration multiplies every old problem. Precision landings matter more when you aim for the South Pole, near craters that may hold water ice. Safety margins must cover months and years, not just a few days. Small risks that Apollo could accept become mission stoppers when you plan repeat flights. A tiny leak, a stiff joint, a rough sight, or a strong solar storm can ruin a season. Start with distance. The moon is close by cosmic standards, yet far beyond low Earth orbit. A radio message takes almost 3 seconds for a round trip. That delay is short in conversation, but long when a lander is dropping toward rocks. No one on the ground can joystick a landing in real time. The spacecraft must see the ground, choose a safe spot, and guide itself. Modern landers carry LiDAR, terrain cameras, and software that match what they see to maps. Then there is radiation. Outside Earth's protective bubble, crews face a steady drizzle of high-energy particles and the threat of sudden solar storms. One strong storm can deliver a dose that matters for people and electronics. Long stays force careful planning. Spacecraft need storm shelters, early warning, and materials that cut dose. Mission timing must respect the space weather cycle. Now the dust. Apollo astronauts talked about it constantly. Lunar dust is sharp, clingy, and gets into everything. It can scratch faceplates, jam seals, and carry an electric charge that makes it stick to tools and suits. Kick it up near a lander, and it can sandblast hardware. A sustainable program needs dust-tolerant hinges, filters, and seals. It needs ways to keep dust off suits and out of cabins. It needs landing pads or descent profiles that push less plume toward gear. Landing itself is a challenge. Unlike Mars, the moon has no air to parachute through. Engines do all the work. That burns propellant and sprays hot exhaust across fragile terrain. Lighting near the poles is tricky, with low sun angles that stretch shadows. Add the need to touch down within walking distance of science targets or power sources, and difficulty jumps. Artemis answers with hazard detection, throttled engines, and disciplined landing zones. So what is different in the Artemis era? 3 big things. First, infrastructure. Apollo flew direct and fast. Artemis builds a bridge. The Gateway Outpost gives a repeatable place for crew to meet a lander, swap gear, and wait for windows. It starts small and grows as missions add parts. Second, reusability. Human landing systems are designed to fly more than once, to refuel, and to be upgraded. That spreads cost over many missions and lets engineers fix what breaks. Third, partnership. Agencies and private companies share cost, speed up innovation, and create multiple paths to the surface. The destination is also new. Apollo stayed near the equator. Artemis aims for the South Pole, where sunlight grazes mountain tops and deep craters hide ice in permanent shadow. If we can harvest even a little of that ice, we can make water, oxygen, and maybe rocket propellant. That turns the moon from a remote campsite into a workshop. Each mission lifts less from Earth and does more on location. All of this demands better suits, power, and logistics. Astronauts need flexible joints to carry loads and drill in awkward terrain. Habitats and rovers need energy through the long, cold night. Orion, the deep space cruise ship, must be a reliable ride there and back, with life support that handles long loops around the moon. Ground teams need training that treats lunar missions like a regular cadence, not a one-time stunt. There will be setbacks, schedules will slip, test flights will find flaws, hardware will wear in ways nobody predicted on Earth. But that is the point of a stepwise plan. Each mission buys down risk. Each cargo delivery teaches how dust moves and how power flows. Each crewed flight writes a new checklist that makes the next one safer. If we do this right, the result is not a single headline. It is a living route between worlds. It is a place where nations meet and share data. And it is a rehearsal for Mars, where every problem on the moon appears again, bigger and farther away. In the chapters ahead, we will walk through the hard parts one by one. We will look at radiation and how to manage it. We will tackle lunar dust and how to fight it. We will examine landing hazards, new suits, and the dance between Orion, Gateway, and reusable landers. We will see what must be true for crews to live near the lunar South Pole and come home stronger than they left. Going back to the moon is hard. That is why it is worth doing. Why go back to the moon after half a century? Because the reasons have multiplied. Apollo proved we could arrive. Artemis exists because staying changes everything from science to economics to how nations set the rules for space. The moon is no longer a distant trophy. It is the nearest place where we can learn to live away from Earth and build the tools to reach farther. Start with science. The moon is a time capsule. It has no wind, no rain, and very little geology to erase the past. When a rock records an ancient impact, it keeps that memory for billions of years. By dating layers of lava, ash, and tiny glass beads melted by micrometeors, scientists rebuild the timeline of the inner solar system. That timeline clarifies when Earth was bombarded, when volcanoes were active, and how the sun's output has changed. Each new sample sharpens the clock we use to date surfaces across the moon, and by comparison, across Mars and the asteroids too. Artemis aims for the lunar South Pole for a reason: water, ice. In permanently shadowed craters, sunlight never reaches the ground. Temperatures sink so low that molecules delivered by comets and the solar wind can survive water, hydrogen, and other volatile chemicals. If crews can map that ice, measure its purity, and test small-scale extraction, they can turn it into drinking water and breathable oxygen. Split water into hydrogen and oxygen, and you have the ingredients for rocket propellant. This is not a fantasy. It's a sequence of practical steps. Find it, sample it, process a little, then scale up if it works. If it doesn't, we learn the limits and adjust. Either outcome is valuable. The moon is also a natural lab for physics and astronomy. The far side is radio quiet, shielded from Earth's constant noise. A simple antenna array there could listen to the universe's dark ages, the time before the first stars ignited. Near the poles, stable ridgelines and long lines of sight are ideal for laser communications and optical navigation tests. Seismometers can probe the moon's deep interior, telling us how small rocky worlds cool and crack. Dust and radiation sensors can capture the real environment. Crews will live in data you can't fake on Earth. Every instrument we place builds a fuller picture of the neighborhood we share with the moon. Now the economics. When the first satellites launched, there was no space economy. Today there is. Launches, weather, navigation, imaging, communications, all woven into daily life. The next layer is cislunar space, the vast volume between Earth and the moon, and the region around the moon itself. If travel becomes regular, A network follows. Think navigation beacons for precision landings. Relay satellites so habitats and rovers can talk to Earth around the clock. High-resolution maps that guide autonomous vehicles. Fuel depots at staging orbits. Cargo services that deliver packages of tools, food, and spare parts to specific landing zones. Reusable landers will need routine propellant resupply. Power providers could test solar arrays on sunlit ridges and beaming concepts that send energy to shadowed sites below. Each piece lowers the cost of the next piece. Value also flows back to Earth through technology. Lighter materials, smarter batteries, radiation-tolerant electronics, dust-proof bearings, and autonomous landing software are obvious examples. Medical systems designed for long missions improve remote care at home. Water recycling and air purification built for habitats can make desert towns more resilient. Rugged robots that tolerate grit and heat help mines and farms. History is clear. When you push engineering in space, you discover solutions that matter on the ground. Politics is a third driver, and it is about norms as much as flags. Who sets the rules for how spacecraft approach each other? How do teams share positions to avoid interference? How do we protect historic sites and sensitive science areas? What counts as due regard when multiple missions want the same ridge with near-constant sunlight and nearby ice? Artemis answers with partnerships and published principles, transparency, interoperability, safety, and respect. The more countries that operate under shared expectations, the safer and more predictable the moon becomes for everyone. There is also straightforward geopolitics. Other major powers have active lunar programs and plans for long-term presence. That competition is not a reason to rush, but it is a reason to show up and lead with openness. If the United States and its partners demonstrate that safe, peaceful, reusable exploration is practical, it sets a powerful standard. It says that going outward is not a grab for resources, but a shared effort to learn, work, and build. The best way to make that statement real is to fly often, share results, and invite others into a framework that rewards responsible behavior. Timing helps. 4 trends matured together. First, heavy lift rockets and deep space crew capsules are coming online. Second, private launch has driven costs down and cadence up, so cargo can fly on a different schedule than crew. Third, autonomy sensors, mapping, and guidance has advanced enough to attempt precision landings near rough, interesting terrain. And fourth, international coordination is stronger, with more agencies and companies ready to add modules, instruments, and logistics. Put together, those trends make sustained lunar operations realistic rather than theoretical. What about risks and costs? They are real. Spaceflight is hard, and budgets are finite. That's why reusability and modular design matter. A lander that flies again lowers cost per landing over time. A small station in lunar orbit lets us upgrade one piece at a time instead of rebuilding the whole stack. An open supply chain invites multiple providers to compete on price and reliability. Step by step, you move from heroic one-offs to regular service. There is also a human reason we rarely say out loud: practice. People learn by doing, not by simulating forever. The moon is close enough to reach in days, but far enough to stretch every system. If something fails, rescue or return is still possible within a mission timeline. Crews learn to live with delay, isolation, dust, radiation, and extreme temperature swings. They learn to schedule work around long days and longer nights. They learn what to automate and what to keep manual. That experience is the ticket to Mars. Finally, inspiration matters. The first images of Earth from lunar distance changed how people saw our planet. A new generation will grow up with live views of the South Pole, with crews walking along razor-edged crater rims, with route maps between outposts. classrooms will track experiments that melt ice samples and 3D print landing pads. Students will see real jobs, welding, geology, robotics, medicine, flight operations reflected in lunar work. Steady progress, visible to all, builds public patience in a way a single flag never could. So why return now? Because the moon is the most accessible proving ground for everything humanity wants to do in space. It's where we can test life support, practice precision landings, map resources, and write the rules of the road. It's where science will answer basic questions about our neighborhood. It's where industry will learn what off-world logistics actually means. And it's where nations can show that exploration and responsibility can live together. Artemis is not about repeating history. It's about building the first reliable road between worlds. Radiation is the quiet danger of deep space, the kind you can't see or feel until the dose adds up. Low Earth orbit is a cocoon wrapped in Earth's magnetic field. Astronauts on the space station still get more radiation than we do on the ground, but the planet's shield knocks the worst of it away. Artemis crews will step outside that shield. The rules change the moment you pass the edge. There are three main sources to think about. First, galactic cosmic rays, fast, heavy particles that drift in from supernovas and other violent events across the galaxy. They are relentless, like a fine sandblasting of energy that never stops. Second, solar energetic particles bursts from our own star during flares and coronal mass ejections. These come in spikes, the kind of storm that turns a quiet day into a high-risk hour. Third, the Van Allen radiation belts, donuts of trapped particles around Earth. They are local to our planet, and a spacecraft must cut through them on the way out. A smart flight path spends the least possible time in the belts. Apollo did this by picking a narrow corridor that darts through thinner regions. Artemis does the same. It's minutes to hours of exposure rather than days. Once outside, the belts are behind you, and the long cruise to the moon begins under the steady drizzle of cosmic rays. Cosmic rays are hard to stop. Heavy metals like lead sound strong, but high-energy particles can smash into dense atoms and produce a spray of secondaries. What works better is hydrogen-rich material water, polyethylene, and certain plastics which spreads the energy out with less shrapnel. Spacecraft already carry water, food, and supplies, so engineers use them as part of the shielding. Tanks can double as a wall. Storage bags can form layers. Inside Orion, designers planned a storm shelter, a small zone where the crew can huddle behind stacked water and provisions if the sun erupts. That's the second threat, solar storms. They are rare on the timescale of a mission, but not rare enough to ignore. A big event can push dangerous levels of radiation through a thin suit in hours. The key is forecasting and warning. We now watch the sun from multiple spacecraft and ground networks. When a flare launches a cloud toward Earth and the moon, analysts can estimate arrival time and strength. If a storm is on the way, crews suspend spacewalks, power down sensitive instruments, and move into the most shielded part of their ship or habitat. The rule is simple: never be caught in the open when the sun goes wild. Choosing when to fly also matters. During the active years of the solar cycle, storms are more likely, but the background of cosmic rays is lower because the sun's magnetic bubble is puffed up and pushes some of the galaxy's particles away. During quiet years, storms are less common, but cosmic rays climb. There is no perfect window. Mission planners balance one risk against the other, update with current space weather data, and make sure every vehicle has a safe place to ride out an event. The moon itself offers no protection. There is no global magnetic field to bend particles aside, no air to slow them down. A habitat or rover is the shield. That is one reason Gateway, the small outpost planned for a near rectilinear halo orbit around the moon, matters. It's not just a transfer point, It's a controlled, monitored environment with built-in shielding and instruments that log the radiation field hour by hour. With data streaming continuously, teams on Earth can refine models, test materials, and learn how dose builds up during real operations, not just in ground labs. We got an early look at this environment during the uncrewed Artemis I flight. Phantom torsos packed with sensors rode inside Orion, one wearing a radiation protection vest, one without, to map where particles penetrated and how much shielding helped. That kind of test is invaluable. It tells us which corners of a cabin need extra material and whether a vest is worth its mass when the sun pops off. It also trains the software that predicts cumulative dose for real crews. Suits are the weak link. Spacewalk suits are designed for mobility, dust protection, thermal control, and life support. They are not radiation bunkers. When mission control sees elevated solar risk, the answer is not a thicker suit. It's a different plan. Keep EVAs short. Stay near a vehicle or habitat so you can retreat fast. Schedule high-exposure tasks for calm windows. Carry personal dosimeters that chirp your dose in real time and set limits that trigger an immediate stop. Radiation is not only a crew problem. Electronics can glitch or fail when a single particle flips a bit in memory or punches through a component. Designers use rad-tolerant chips, error-correcting software, and redundancy. They put the most sensitive gear behind extra material. Critical systems get multiple, independent paths, so a hidden one does not cascade into a mission-ending failure. Over months and years of Artemis flights, engineers will compare predicted failure rates against reality and harden the next round of hardware. Medical risk is statistical. A single mission dose may be well within limits, but risk accumulates across a career. Policies set maximum lifetime exposure, adjusted by sex and age, because cancer risk is not the same for everyone. That's why collecting precise dose histories matters. Every astronaut's file will include not just a total number, but when that dose happened, under what spectrum of particles, and through which materials. In turn, that record guides future assignments and informs informed consent. What about medicines or radiation cures? For now, the best protection is still operational. Minimize exposure, shield smartly, and know when to shelter. There is ongoing research into radioprotective drugs and gene-level responses to radiation, but nothing is ready to replace good shielding and careful timelines. The moon is where we will learn which countermeasures actually help in a real habitat with dust, heat swings, and astronauts who still need to move, work, and sleep. When you add it up, Artemis approaches radiation like every other lunar hazard. Design out what you can, prepare for what you can't, and build margins into the plan. Pick fast crossings through the belts. Equip Orion, Gateway, and landers with flexible shielding and a storm shelter zone. Watch the sun with better eyes than any program before. Carry sensors on the crew, on the walls, and even buried in the regolith near camp to understand how particles change over a day. Teach crews to treat radiation like weather, check the forecast, bring the right gear, and never ignore a warning. There is no way to make deep space perfectly safe, but there is a way to make it safe enough to work, to learn, and to come home. If we can turn radiation from an unknown into a managed, measured factor, then one of the biggest reasons we left the moon for 50 years will become one more problem we know how to live with. Lunar dust is the moon's most stubborn problem. It looks soft in photos. It is not soft. The regolith is rock shattered by billions of impacts and flash melted into glassy shards. With no wind or rain to round it off, each grain keeps knife-like edges. Think powdered glass with static cling. Those grains stick, scratch, and creep into hinges, zippers, and seals. Apollo crews complained about dust more than almost anything else. They tracked it inside, tasted it in the air, and watched it dull visors. Why does it stick? On Earth, dust rides air. On the moon, there is none. Ultraviolet sunlight knocks electrons off grains, and rubbing adds charge when boots scrape the ground. Charged, jagged particles latch onto fabric and metal and hook into fibers. Even after brushing, a thin film often stays behind. Sharp grains do damage fast. Micro scratches on a visor scatter light and kill contrast. At the South Pole, where the sun sits low and shadows are long, glare can turn a simple walk into a hazard. Dust also eats moving parts. Seals, bearings, and fabric joints lose their smooth finish and begin to leak, squeak, and seize. Radiators and solar panels fade when a gray coat settles on them. On Earth, a hose fixes a dirty panel. On the Moon, water is precious, and blasting dust just throws grit into other gear. There are health concerns, too. In the Apollo era, one astronaut compared the smell to spent gunpowder. Another reported hay fever-like symptoms after a dusty EVA. We still do not fully know how lunar dust affects lungs over weeks or months. The grains are fine enough to reach deep airways, and their surfaces can irritate tissue. Until the risks are mapped, Artemis will treat dust as a potential toxin. That means strong cabin filters, masks in the airlock when needed, and cleaning that keeps living areas clear. How do you fight a material that sticks, grinds, and drifts into everything? First, stop it at the door. A good airlock is not just a hatch. It is a system with zones, a dirty side for suits and tools, a clean side for people and air. Vacuum lines, brushes, and adhesive rollers live in the dirty zone. A gentle gas jet, not wasteful, just enough to lift particles, loosens what static holds, filters trap dust before air crosses into the cabin. The rule is one way. Suit comes in dusty, person crosses over clean. A bolder approach is to keep suits outside entirely the suitport. The suit mounts to the outer wall like a backpack. An astronaut steps in from the back, seals it, and walks out to the surface. Returning, they dock the suit, unlatch, and step straight inside. Suitports demand reliable ring seals and precise alignment. But if they work, they cut the problem where it starts. Dust never enters the habitat. Second, give surfaces a way to shed dust on their own. Electrodynamic dust shields use transparent electrodes to create traveling electric fields that push charged grains away. Built into visors, camera windows, and solar arrays, they can clear a view in seconds. It is not magic, it takes power. And it works best on charged particles, but on the Moon, most grains are charged for part of the day. So the method can do real work. Third, design hardware with dust in mind from day one. Bearings get labyrinth seals and sacrificial covers. Connectors get sprung caps you can flip with a glove. Cables and hoses route, so gravity helps shed grit. Textiles use fibers that snag less and coatings that reduce adhesion. Tools avoid deep crevices and knife-edge transitions that trap powder. Even labels matter. Etched plates beat stickers that curl and collect dirt. When the environment tries to poison every moving part, the best defense is simple parts with big margins. Fourth, change how you land. Rocket exhaust accelerates grains like sandblasting media and throws them far. As a base grows near a landing zone, plume erosion threatens windows, panels, and instruments. Fixes include landing pads, pre-delivered mats, or pads made on site by melting or sintering regolith and plume-friendly descent. Throttle softly, split thrust across more nozzles, avoid low hovers, and pick sites with natural shielding. Operations matter as much as hardware. Crews will mark dirty paths and clean zones. Rovers park downwind of arrays and radiators. Wheels are shaped to throw smaller rooster tails. Samples get bagged at the source, double-bagged before the airlock, and opened only in a filtered glove box. EVA timelines reserve minutes to clean tools before stowage. Thermal and charging cycles complicate everything. Dust does not melt like snow, but parts shrink and expand from day to night. A joint that is tight at noon may open at night. Dawn and dusk can flip surface charge and make grains jump. Procedures must adapt to morning, midday, and twilight. The moon is slow, but it changes with the light. There is an upside. Dust forces better engineering. A hinge that laughs at grit will work in mines, deserts, and disaster zones on Earth. A habitat that stays clean and powder can improve hospitals and clean rooms. A lander that touches down without sandblasting the neighborhood sets a pattern for safer spaceports on the moon and beyond. Artemis treats dust the way climbers treat rotten rock, with respect, not fear. Early missions will test coatings, suitports, electrodynamic shields, and landing mats, then report honestly about what fails and what holds up. Upgrades will fly quickly, and procedures will evolve. The goal is not to keep the moon spotless. The goal is to work there without grinding our equipment and our crews to pieces. Success will sound boring, and that is the point. After a week on the surface, a crew should come home with clean lungs, clean data, and hardware ready to fly again. When that becomes routine, dust will still be everywhere, but it will no longer be the headline. It will be the ground we stand on while we do the real work. Landing on the moon is a ballet with no music, only numbers. There is no air to glide through and no parachute to buy time. Engines do everything: brake, steer, and hover, while computers watch the ground for rocks that could end a mission in 1 second. It feels like 7 minutes of terror stretched into a quiet, relentless focus. Nothing screams. Everything must simply work. Picture the sequence. The lander undocks in lunar orbit and checks its health. A short deorbit burn lowers the path toward the target. Then comes powered descent initiation, or PDI. The main engine lights. Velocity unwinds. The lander rotates so its eyes can see forward and down, not just the sky. Guidance splits the drop into phases. First is braking, bleeding off most of the sideways orbital speed. Second is approach steering toward the landing zone while correcting small errors. Third is terminal descent. Meters per second becomes centimeters per second while the lander searches for a clean patch of ground. Each phase has gates. If sensors disagree or fuel reserves hit a limit, the computer waves off and climbs to orbit for another try. What does the lander see? In deep space, an inertial unit and star tracker keep attitude. Near the moon, you need position over the ground. That is where terrain, relative navigation, comes in. Down-facing cameras grab rapid images of craters and ridges and compare them to onboard maps. When the view matches, the computer knows its position to within meters. LiDAR or radar adds altitude and velocity with laser-precise readings. Navigation Doppler LiDAR sends a few narrow beams and reads the frequency shift to measure 3-axis velocity. At the South Pole, lighting is a puzzle. The sun skims the horizon. Shadows run like canyons, hiding boulders and pits. The answer is multiple eyes, visible, light cameras for bright rims, infrared for shadowed slopes, and LiDARs that ignore darkness entirely. Software fuses it into a hazard map and ranks touchdown spots by slope, roughness, and risk. If the best spot is a little to the left, the lander nudges that way if fuel allows. Fuel is the quiet tyrant. Every meter per second you cancel costs propellant. Every second you hover sands the tank lower. Designers build margin extra propellant for the unknown, but margin is not a wallet. It is a fence that keeps you from running out. If a perfect site is too far, the lander chooses a good one closer. If nothing looks safe, the right answer is to climb away and try again on another orbit. Throttle matters. On the moon, you cannot glide. You must push against gravity with thrust that can go low without coughing out. That is why lunar engines throttle deep down to a small fraction of full power without losing stability. Multiple nozzles spread plume forces and give control if one unit misbehaves. Small reaction jets steady attitude while the main engine kills speed. Then there is dust. As the engine bites the surface, Hot exhaust accelerates grains to bullet speeds. The plume can excavate a hole under the nozzle and sandblast nearby equipment. Worse, dust can blind sensors. Designers counter with higher eyes, sensors on mast's LiDAR that looks through the brownout, and descent profiles that avoid long ground skims. Over time, pads made from melted regolith will help. Early on, smart approaches and brief hovers carry the load. Communications add another layer. Round-trip light time between Earth and the Moon is about 2.5 seconds. That is short for talk, but forever for piloting. No one can joystick a lander through rocks from Earth. Human pilots still matter. Inside the cabin, they can select a new aim point or command an abort. But the default is supervised autonomy. The system flies the profile. The crew and mission control watch trends, set limits, and step in only when the computer asks. Navigation needs fallbacks. If the camera cannot lock onto landmarks because of glare, the radar carries the load. If radar gets confused by rough terrain, LiDAR steps in. If one sensor dies, the system estimates state from the rest. The lander's brain runs parallel computers, so one upset does not freeze guidance. Power buses are cross-strapped. Valves and igniters are redundant. On descent, redundancy is not luxury, it is survival. Maps are the quiet hero. High-resolution terrain models built from orbit let the computer know what should be under it before arrival. During descent, the camera updates that model, catching details smaller than any satellite can see. A boulder, a pit, a fragile outcrop the legs must avoid. After landing, those same maps help the next mission refine its aim and narrow the ellipse. Abort modes deserve respect. If an engine hiccups below a certain altitude, landing is off the table. The crew rolls to a safe pitch and burns for orbit, where a ride home waits. That decision cannot be a debate in the cockpit. It has to be a trigger the computer recognizes and executes. Clear lines, land, divert, or abort keep a demanding job simple under stress. Does a pilot still land the ship? Yes, but differently. The pilot commands intent, accept a sight, ask for a slight offset, call a hold if something looks wrong. The machine handles the millisecond math. Think of it as a dance where the human leads with choices, and the computer keeps the beat. When the legs finally touch, sensors confirm weight on pads, throttles close, and the vehicle settles a breath. Dust falls in a gray curtain, telemetry calms. Outside, the lunar surface is the same as it has been for billions of years. Inside, heartbeat by heartbeat, 100 small decisions add up to one gentle contact. The next landing will go a little smoother because this one taught us where the invisible edges are. Lunar landing will never be casual. It is a careful conversation between fuel, sensors, software, and human judgment. Artemis turns that conversation into a repeatable script, so crews write new chapters on the ground, not in the descent. Artemis is not a single vehicle, it is a team of vehicles and a team of teams. NASA sets the goals and the safety rules. Industry builds much of the hardware under fixed price, milestone contracts that reward results. International partners contribute critical pieces that make the system stronger and more affordable. Think of it like building a railway. The locomotives, the stations, the tracks, and the maintenance crews come from different groups, but the schedule and the standards are shared. Start with the crew ride, Orion. It is the deep space capsule that carries astronauts from Earth to lunar orbit and home again. A heat shield rated for lunar re-entry brings the crew through the intense return from the Moon. The European service module behind it, built by ESA, provides power, water, air, and the main engine pushes. Orion is the taxi between worlds. It does not land. It delivers people to a staging point, then brings them back. To reach space, Orion sits on top of a heavy-lift rocket. That rocket does the brute work of escaping Earth and setting a precise path to the Moon. The point is reliability and performance for the crewed climb. Cargo can fly separately on commercial rockets, but the people get the most margin and the simplest ascent profile. Keep the critical path for humans clean. Move everything else off it. Now the part that makes this era different. The landers are commercial. NASA buys a service. Take our crew from lunar orbit to the surface and back, and lets companies design the best way to do it under tight safety rules. One path uses a large, reusable lander that is refueled in space so it can make multiple trips. Another path develops a different lander with different engines and staging. Two providers mean competition, backup options, and faster upgrades. If one system pauses, the other can still fly. In practice, a landing mission feels like a relay. Before the crew arrives, the lander is already in lunar orbit, checked out, and waiting. Cargo may arrive even earlier at the landing site. Science gear, power kits, communications, beacons. The crew launches on Orion, cruises to the moon, and docks either directly to the lander or to a small station in lunar orbit called Gateway. After checkouts, two astronauts transfer to the lander, ride down, work on the surface, then rise back to orbit and reunite with Orion for the trip home. Gateway is the quiet force multiplier. It will fly in a near rectilinear halo orbit, a stable path that keeps line of sight to Earth and easy access to the South Pole. It is not a giant station. It is a compact outpost that acts like a spaceport and a safe room. It gives crews a place to live between surface sorties, a hub to plug in new modules, and a lab to run instruments for months at a time. It also provides docking ports, power, communications, and a sheltered volume where astronauts can wait out solar storms. Over time, partners will add pieces: a habitation module, a refueling or communications module, robotics to move cargo, better power, and life support. It starts small, then grows as missions demand. International collaboration is baked into the architecture. ESA builds Orion's service module and key gateway elements. JAXA supports habitation and plans a pressurized lunar rover with Toyota so astronauts can travel far and stay warm during the cold. The Canadian Space Agency provides a new generation of robotic arms for Gateway to capture vehicles, move experiments, and inspect the station. Other partners contribute logistics, instruments, and surface systems. These are not symbolic flags. They are mission-critical parts that raise capability and spread cost. Closer to the ground, NASA also runs the CLPS program, Commercial Lunar Payload Services. These are small, fast cargo deliveries to the surface, flown by private landers on private rockets. They scout landing sites, test drills and communications, measure dust and radiation, and deliver science before crews arrive. CLPS lets the program learn cheaply and often. If a payload fails, another flies soon after. The cadence teaches more than any single perfect mission could. All of this sits on a different style of buying spaceflight. Apollo used cost-plus contracts, where the government pays the bill and the contractor is reimbursed for costs plus a fee. Artemis uses more fixed-price milestones where the company only gets paid when it hits a tested, verified target. That approach pushes speed and creativity, but it also demands clear interfaces and strict safety gates. NASA keeps final authority on crew safety and mission rules. Companies carry more design freedom and more risk, and they win by meeting performance at lower cost. Reusability is the engine of affordability. If a lander can be refueled and flown again, the second and third landings are cheaper than the first. If the same avionics box can slide into a cargo variant and a crew variant, spares become simpler. If a docking standard works across Orion, Gateway, landers, and cargo tugs, the team can swap partners without rewiring the whole stack. Common ports, common data links, and common rendezvous rules turn a collection of vehicles into a true transportation system. Mission design respects human limits. No marathon spacewalks on day one. Early landings are short, focused, and supported by pre-placed gear. Crews practice on analog sites on Earth with real tools and real procedures, then fly the same playbook on the Moon. Autonomy handles fine guidance and hazard detection. People handle judgment calls and complex tasks. The goal is rhythm: plan, deliver cargo, fly crew, land, work, leave, review, upgrade, repeat. Redundancy runs throughout. 2 lander families reduce single-point failure at the architecture level. Inside each vehicle, critical systems have backups and fault-tolerant software. If a sensor misbehaves on descent, another takes the lead. If a propellant valve sticks, cross-strapped plumbing reroutes flow. Abort options are rehearsed, and automatic triggers are preset. Try again next orbit is a valid plan, not a shame. Transparency builds trust. Partners share trajectories, frequencies, and landing zones, so vehicles do not interfere with each other. Artemis Accords principles open data for science, emergency assistance, safe disposal, and protection of heritage sites set norms that make the lunar neighborhood more predictable. The program shows its homework, test results, lessons learned, and interface specs that newcomers can use. There will be friction, hardware slips. Interfaces take time to standardize. A shiny new idea will fail its first dusty trial. That is expected. The solution is cadence and iteration. Fly often enough that a bad day becomes data for the next flight, not a program-ending event. Keep modules small enough and contracts flexible enough that better parts can replace weaker ones without pausing the whole line. If this works, the Moon becomes reachable on a schedule, not a headline. A reusable lander waits in orbit, topped off and healthy. Gateway hums with quiet power. Orion arrives, docks, and hands 2 people to the surface for focused work, while 2 stay in orbit to manage the stack. A week later, everyone comes home with samples, maps, and checklists marked in pencil and dust. A few months later, the next crew flies a refined plan with upgraded parts. That is how exploration becomes infrastructure. In the next section, we'll step inside Gateway and see how a small outpost can remake lunar operations by adding a safe harbor, a staging point, and a laboratory that keeps working long after a crew has gone home. Gateway is a small station with an outsized job. It is the porch light over the lunar South Pole, the place where crews meet their lander, swap gear, and catch their breath between surface trips. It is not an ISS-sized city. It is a compact loft, 1 pressurized room to work and sleep, a power and propulsion bus to move and keep station, docking ports, a robot arm, and racks for science that keep running when nobody is aboard. Its path looks odd. A near rectilinear halo orbit, a long lopsided loop that swings close to the Moon on one end and arcs far away on the other, while staying in steady radio view of Earth. That shape is a tool. The close pass makes South Pole landings efficient. The high arc gives nearly constant sunlight for power and clean communications with Earth and surface crews. The orbit is stable enough that gentle electric thrusters can hold it for years without guzzling propellant. 2 core pieces make Gateway tick. The power and propulsion element is the tug and the electric utility. Large solar arrays feed high-efficiency electric thrusters, quiet engines that sip xenon and nudge the whole outpost. They do not shove. They push patiently, ideal for station keeping and slow relocations. The Habitation and Logistics Outpost, or HALO, is the first living space, workstations, bunks, life support, a compact galley, avionics, and an airlock. From that seed, partners add capability. A European module expands living space and deep space avionics. A refueling and communications module adds tanks, plumbing, and extra links. Japan contributes life support upgrades and interfaces for a future pressurized rover, so crews can range far and still return to a warm cabin. Canada's next-generation robotic arm patrols the exterior, catching visiting cargo ships, inspecting arrays, and moving experiments like a careful crane. Standard docking turns Gateway into a true port. Orion can dock on one side, a human landing system on another, while cargo tugs park pallets until crews arrive. Multiple ports let people swap vehicles without pulling the stack apart. That flexibility matters when a solar storm says, "Wait," or when a lander needs a few extra orbits before it is ready to descend. Inside, Gateway feels like an efficient workshop. Racks host radiation monitors, communications testbeds, navigation beacons, and small science payloads that love steady power and long observation windows. One corner is the storm shelter, the densest patch of shielding where the crew can ride out a solar event behind water and supply bags. Space is tight, so every surface works. Fold-out desks, stowable exercise gear, and smart storage. Operations are built for cadence. Most of the time, Gateway flies empty on autopilot. It keeps power, points arrays, logs, radiation, and checks its own health. When a mission starts, the outpost wakes. Orion arrives with a crew. Systems are reviewed. Then a lander shows up from staging orbit or from the surface. Cargo moves through the arm or through pressurized tunnels. 2 astronauts transfer to the lander while the others remain at the outpost to manage the stack, answer checks, and plan the return. Why not skip Gateway and dock Orion straight to a lander every time? Sometimes that will happen, but the station makes the system resilient. It is a safe harbor if space weather or hardware says, "Hold." It is a backbone for communications and navigation. It gives engineers a repeatable place to plug in new instruments for months without tying up a cruise ship. It lets multiple providers design to one set of interfaces instead of custom fitting to each other. Over a decade, that standardization saves money, reduces risk, and speeds upgrades. The orbit itself is a teacher. Flying in deep space around the moon tests the autonomy and fault tolerance we need for Mars. Electric propulsion logs years of runtime and refueling cycles. Thermal systems learn to handle long swings between hot and cold as the outpost loops high and low. Communications teams refine laser links and relay protocols that must be rock solid when crews are below the horizon. Even simple habits, how often to exercise, how to sleep well without sunrise cues, how to manage workload without ground's constant hand on the loop, get tuned for long missions far from Earth. A typical visit might install a new docking adapter, release a small satellite to scout a future landing site, and test fuel transfer between a tanker and a lander, a rehearsal for true reusability. Crews might calibrate a dust sensor that watches for plume grit lofted by nearby landings, while long-duration instruments keep collecting radiation data to refine suit limits and EVA schedules. None of this has to finish in one lunar day because the outpost can host experiments for months and hand them off from one crew to the next. Safety threads through every function. Redundant communications routes mean a single antenna loss never silences the station. Cross-strapped power and avionics keep guidance alive, even if a box goes dark. The robot arm can survey a panel humans cannot reach. If a lander waves off, it can loiter at Gateway where air, power, and advice are close. Medical kits and telemetry let flight surgeons track crew health in deep space with more context than a brief surface pass could ever give. Gateway is modest on purpose. A smaller outpost is faster to build, cheaper to launch, and easier to upgrade. It is big in the way that matters. It changes how we operate. It anchors a route between Earth and the lunar surface. It lets missions overlap. It keeps science alive between crews. And it builds the muscle memory of living just beyond the cradle, where Earth is still in view but no longer the only home we know. In short, Gateway turns lunar exploration from a string of sprints into a sustainable relay. With a light always on above the South Pole, crews can come and go, missions can overlap, and the moon starts to feel less like a one-off destination and more like a place where work gets done. Reusable lunar landers are the workhorses of Artemis. They turn a rare stunt into a service. A lander that can fly, refuel, and fly again changes everything. Costs drop, schedules speed up, and each mission teaches the same machine new tricks. Think of them as trucks in the sky, shuttling people and cargo between orbit and the surface, again and again. Two design families dominate. One is the single tall ship, a large vehicle that descends, ascends, and houses life support in one body, topped off by refueling in space. The other is the two-piece style, a stout descent stage that takes the dust and rocks, and a light ascent cabin that returns the crew to orbit. The two-piece approach can leave a platform on the ground for power and cargo, while the cabin cycles back to orbit. Refueling is the breakthrough both need. In space, the gas station is a tanker that meets the lander in orbit and transfers super-cold propellants. That transfer is delicate. Liquid oxygen and either methane or hydrogen must stay cryogenic, otherwise they boil away. Engineers fight boil-off with sunshades, foam insulation, radiators that face deep space, and tight plumbing with zero boil-off heaters, so liquids stay calm during docking and long engines drive the rest. Lunar engines must throttle deep, restart reliably, and burn cleanly so sensors can see through dust. Hydrolox hydrogen with oxygen offers high efficiency but needs bulky tanks and precise thermal control. Methalox methane with oxygen packs tighter and is easier to store at a small performance cost. What matters most is controllability. Hover lightly, sidestep a few meters, then push hard to climb. Reusability starts at the legs. Pads absorb touchdown and keep the belly off rocks. They need crushable material for hard contacts, a wide stance for slopes, and covers that deploy before the plume starts digging. Some designs add tiny tip thrusters to steady the last few meters. When it is time to go, pads must peel cleanly from soil. The exhaust has compacted like concrete. Cabins are small houses with a job. They need room for suits, racks, a compact galley, and toilet, plus an airlock that opens to the surface without dragging dust inside. Windows resist scratches. Cameras provide most of the view. Life support stays simple. Short missions, generous filters, parts sized for gloves. Comms run through a steerable high-gain antenna with backups to a relay or to gateway. Cargo variants are the unsung heroes. Without people, a lander can carry heavier gear, pallets with solar arrays, rollout radiators, drills, small rovers. It can act as a crane, lowering boxes or setting them a safe distance from the plume. Over time, a site fills with the right tools. When crews arrive, they focus on science and assembly instead of backpacking everything. Docking is where reuse meets rhythm. A standard ring and a common rendezvous playbook let any cruise ship meet any lander at gateway or directly in lunar orbit. Refueling uses similar standards for valves, data, and safety checks. The more common the interfaces, the faster the handshakes. A lander undocks, descends, returns, docks, powers down for inspection. A tanker tops it off. The cycle repeats. Thermal control separates paper designs from real vehicles. Sunlight near the South Pole can be relentless on ridgelines and absent in shadows. Landers use blankets that act like a thermos. Radiators sit where they can see cold space without gathering dust. When parked, a lander can yaw to spread heat or point sensitive bits into shade. Inside, heaters keep valves, batteries, and computers in their happy range. Plume effects shape every landing plan. Hot exhaust accelerates grains into high-speed spray. If a base grows near the zone, that spray can threaten windows and arrays. Engineers tame the plume by splitting thrust into smaller jets, angling exhaust to reduce scouring, or aiming for pads built from sintered regolith. Early missions will test pre-delivered mats and microwave melted strips. The goal is simple: do not sandblast your own front door. Autonomy carries a heavy load. Terrain relative navigation compares real-time images to onboard maps and picks safe spots, or measures slope and roughness in the dark. If something looks wrong, the computer diverts a few meters. Humans can approve or override, but the machine handles the millisecond decisions. On ascent, the same system lines up the rendezvous and steers into the capture box for docking. Maintenance is the quiet win of reuse. Between flights, teams inspect seals, swap filters, and update software. Fault logs show which parts run hot or which valves cycle too often. The second flight fixes issues found on the first. By the fifth, the vehicle hovers less, throws less grit, and burns a cleaner path to the pad. Learning compounds and costs bend downward. Safety lives in options. Abort modes exist at every phase. Return to orbit if a leg sensor fails. Divert to a nearby site if rocks appear. Loiter at gateway if a solar alert pops. Redundant avionics vote on guidance. Cross-strapped power keeps thrusters alive, and independent communications paths prevent a single antenna from ending a mission. Looking ahead, reusability opens doors. If ice at the poles can be mined and split into oxygen and hydrogen, a future depot at Gateway could top off Hydrolox landers with lunar-made propellant. If methane is favored, oxygen from lunar regolith still halves what must come from Earth. A printed pad, a small crane, and a covered garage for rovers sound like luxuries now. After a few flights, they become obvious steps to protect people and hardware. In the big picture, a reusable lander is not a trophy. It is a bridge piece. It links Earth launch to lunar living. It lowers costs, raises cadence, and turns landing from a cliff-edge event into a practiced service. When crews step off the ladder and the vehicle waits patiently for the ride home, that quiet confidence is the clearest sign the moon has moved from discovery to operation. A spacesuit is not clothing. It is a tiny spacecraft wrapped around a person. On the moon, that ship must keep you alive, let you work, and help you come home without slowing you down. Apollo suits proved we could walk and collect samples. Artemis suits have a bigger job. Longer stays, rough South Pole terrain, and harder tasks like drilling and assembling gear. The leap is mobility, dust control, fit, and reliability over many outings, so crews can treat lunar work like a repeatable shift, not a one-time stunt. Mobility comes first because work fails if joints fight you. New suits add better bearings at hips, knees, shoulders, and wrists, plus smarter joint patterning at the waist and ankles. Astronauts can kneel, squat, and reach overhead without wrestling the internal pressure bubble. Gloves the hardest part. Gain dexterity from shaped finger joints, refined fabrics, and palm pads that grip tools without crushing circulation. Good hands mean fewer dropped samples, faster connectors, and less fatigue when every motion costs effort. Pressure is a trade. Higher suit pressure is gentler on the body, but makes every bend harder. Lower pressure feels nimble, but demands more pre-breathing, so nitrogen clears and you do not get the bends. Artemis balances this with careful timelines. Crews pre-breathe oxygen in the airlock, then work at a pressure the suit can manage for hours. Inside, fans keep air moving so carbon dioxide does not pool, and sensors track partial pressures to keep breathing steady, even when the pace of work changes. Thermal control never stops. Under the outer shell, astronauts wear a cooling garment, a mesh of thin tubes that carry water over the skin. A backpack loop pulls heat from that water and rejects it to space through heat exchangers. Older sublimators vented a little water as ice flashed to vapor. Newer loops aim to be more regenerative, riding through short heat spikes and dumping heat later to save water. The goal is simple: warm in shadow, cool in sun, without constant fiddling by a tired crew member. Dust is the moon's most stubborn problem, so suits try to keep it out and shake it off. Outer layers use abrasion-resistant weaves and coatings that reduce static cling. Seals are shielded by gaiters and hard rings that keep sharp grains away from moving parts. Zippers and cable runs are simplified, so there are fewer places for grit to hide. Many designs use a rear entry hatch, so the torso acts like a door. It is easier to clean a single ring than a long zipper across a dusty chest. Airlocks add help. Suitports let the backpack dock to the wall, so an astronaut steps straight in from inside, sealing the suit to the outside. The dusty shell stays outdoors. The person enters the clean cabin. Even with a standard airlock, crews use vacuums, sticky rollers, and targeted gas jets to loosen clinging grains. Filters grab what comes off the suit before it drifts into living space, and scripted cleaning keeps the routine fast and reliable at the end of long, cold EVA. The helmet is both window and workshop light. Visors carry gold-coated sunshades to tame glare at the South Pole, anti-scratch layers to survive brush with dust, and anti-fog treatments so breath never clouds the view. Integrated lights help when the sun sits low and shadows run long. Cameras on the helmet and chest record what you see for science teams at home and for later training. Audio is cleaner too, with better noise rejection so the hum of pumps does not drown out a partner's voice. Life support lives in the backpack. Tanks carry oxygen for hours of work, with a reserve for emergencies. Sorbent canisters scrub carbon dioxide. Some cartridges are replaceable. Others can be baked out and reused between EVAs. Pumps circulate cooling water and ventilation flow. Electronics monitor pressures, flows, and battery status and warn early if anything drifts. A simple control panel lets an astronaut tweak cooling, check suit pressure, or switch to a backup scrubber, even with gloved, tired hands. Fit used to be a barrier. Apollo suits were custom. Later designs had narrow size ranges. Artemis shifts to modular parts, torso lengths, leg and arm sizes, and glove sets that mix and match. Hard rings and soft joints adjust, so more body shapes can move freely. Inclusion is not only fair, it is safer. A suit that truly fits reduces fatigue, prevents hotspots and blisters, and keeps the center of mass where the wearer expects it to be on slopes and powder. Interfaces make the suit part of a system. Standard waist ports let a rover plug in air and power for shirt sleeve rides between sites. Common attachment points let cranes or booms catch a crew member during assembly. Quick connects for science boxes prevent fumbling. Radios hop between direct-to-earth, rover relay, and gateway relay with minimal setup. Add clear EVA operations, short checklists, partner rules, mid-task body checks, and the suit fades into the background while the mission takes the lead. Testing makes or breaks all of this before anyone steps on the regolith. Suits spend hours underwater in neutral buoyancy tanks to rehearse movement. They run in thermal vacuum chambers, where lamps mimic the sun and black walls mimic deep space cold. Engineers throw dust simulants at bearings, flex joints until fabric frays, and cycle boots across rocks and slopes. Field trials in deserts and volcanic plains teach how the whole system feels at the end of a long day, not just in a clean lab. In the end, the best suit is the one you forget you are wearing. It moves when you move, protects without fuss, and lets you focus on rocks, instruments, and the horizon instead of valves and warnings. Apollo opened the door. Artemis widens it for real work day after day, crew after crew, until lunar walking feels less like a spectacle and more like a shift well done. Making the moon workable comes down to two relentless forces: high-energy radiation and sharp, static, charged dust. You don't beat them with one trick. You layer defenses until the risk is low enough that people can focus on real work. Artemis treats protection like an onion root: choices and timing on the outside, then materials, habitat design, operations, and finally personal practices at the core. Start with passive radiation shielding, because it's the only kind you can trust every minute. Hydrogen-rich materials are the winners. Water, food, and certain plastics spread particle energy without spawning as much secondary shrapnel as metals do. Designers pack these into the walls where the crew sits most often, turning ordinary supplies into a quiet shield. Inside each vehicle and habitat is a true storm shelter, a small, dense nook built with stacked water bags, stowage, and extra panels where a crew rides out a solar burst. The shelter is boring on purpose. Little volume to cool or heat, one light, a tablet, and calm airflows that don't stir dust. On the surface, regolith becomes armor. A habitat delivered in a can can be buried under bags of local soil or under 3D printed shells fused from the same material. 2 to 3 feet cuts dose. More cuts it further. Early flights will use simple methods. A small bulldozer blade on a rover to throw berms over thin roofs, flexible sandbags filled and stacked by a teleoperated arm. Later, centering rigs melt regolith into tiles that interlock like shingles. The moon turns into its own shield. Active shielding magnetic bubbles or electrostatic fields shows up often in headlines. In practice, it's still experimental. Superconducting coils, high voltages, and complex plasma behavior make for tricky systems with their own risks. For now, the plan is to rely on passive mass and smart operations, and to test active concepts on uncrewed payloads. If a narrow, local, active field ever proves dependable, it might protect a workstation or a rack of sensitive electronics rather than a whole habitat. Protection also means knowing, not guessing. Crews wear personal dosimeters that log dose by the minute. Walls embed sensors that sample the radiation field at different heights and angles. Small spikes teach where the habitat is thin. A probe buried outside watches how dose changes as sunlight and the moon's position shift. All of that feeds a simple rule set, which tasks to schedule when, how often to rest in the shelter, and how to keep lifetime exposure well below limits across multiple missions. Dust control begins with a hard boundary. The surface is dirty. The cabin stays clean. Airlocks become dust locks with a dirty side and a clean side, their own air circulation, and filters that trap particles before air crosses over. Suitports go further. The suit stays outside. Only the person comes inside. A rear entry hatch lets an astronaut step into the torso from the cabin and back out to the surface without dragging grit through a doorway. If a classic airlock is used, the routine is fast and scripted. A short puff from a dedicated gas line to loosen grains, a vacuum pass, a sticky roller on cuffs and boots. Then filters that cycle the lock air through an electrostatic collector before the inner hatch opens. Surfaces learn to shed dust without a brush. Electrodynamic dust shields, transparent electrodes that create traveling electric fields, can sweep charged grains off visors, camera windows, and solar panels with a tap. On larger panels, gentle vibration adds a nudge. Coatings help too. Low adhesion films on fabrics, hard caps on seals, and rounded covers on connectors deny dust the sharp corners it loves. Inside, air returns are placed low, where heavier grains settle, and the flow pattern traps particles in a replaceable cartridge before they can wander. Mechanisms are designed for grit from day one. Bearings sit behind labyrinth seals. Hinges use generous clearances and solid lubricants that don't boil away in vacuum. Valves choose simple motions over clever tricks that fail when dust sneaks in. Cables and hoses route along smooth, accessible paths so a glove can sweep them clean. Even labels shift from stickers to engraved plates because nothing peels like a dirty decal in vacuum. Landing pads matter as much as brooms. Rocket exhaust turns regolith into a high-speed spray. Early crews will roll out tough mats or land on pre-delivered pavers to keep the first plume from digging craters. Microwave or laser sintering can bake strips into hard pavement for wheels and legs. Over time, a full pad is printed with berms that catch any stray grit. Rovers then drive on marked lanes that keep rooster tails away from radiators and arrays, and parking spots sit downwind of anything fragile. Operations are the glue that makes hardware work. EVA checklists include dirty hand, clean hand, rules. Tools that touch soil stay in the dirty zone, get a quick clean before stow, and enter the glove box only after a second pass. Samples move through double bags and open only inside a filtered box. So the science team sees rock, not cabin dust. Crews schedule tasks to the light. At the South Pole, low sun angles make glare harsh and shadows deep, so helmet lights and visor filters are planned, not improvised. Thermal control meshes with dust control. Radiators sit where they see cold space but avoid plume spray. If dust coats a panel anyway, the electrodynamic shield and a short vibration cycle clear enough to keep power high. Placement beats cleaning. Put sensitive gear behind small berms, under overhangs, or on poles above the worst of the rooster tails, and you clean less often for the same effect. The human factor closes the loop. A clean habit is a safe habit. Color-coded zones mark where dust is expected, and a quick glance tells a tired crew member if a white glove just crossed into a black zone. End-of-day routines are short and consistent to help tired brains. Stow, clean, filter, log, rest. Sleep happens in the cleanest corner, away from the lock. Morning starts with a sensor check and a glance at the sun. What is the radiation forecast? What is the windless dust weather? Today, bright, gray, or deep shadow. Put together, these layers do not make the moon gentle. They make it manageable. Radiation drops from an unknown to a measured number with margins. Dust shifts from a creeping poison to a controlled nuisance. The gear lasts longer, the crew breathes easier, and the science gets cleaner, literally and figuratively. This is how Artemis turns harsh into workable. Mass where it counts. Smart materials and simple mechanisms. Maps and sensors watching the environment, and procedures that respect limits. In the next section, we'll zoom out from protection to living, how bases, power, and resource cycles make stays longer, safer, and more productive. Living on the moon is not magic. It is logistics and discipline. A base is a small neighborhood with air, water, power, and trash to handle, surrounded by rock that swings from boiling hot to cryogenic cold. The difference between a heroic visit and a livable outpost is simple. Close the loops, smooth the peaks, and design every routine so tired people can do it right the first time, every time. Start with the habitat. Think of a strong can that arrives airtight, then grows tougher with local material. The shell lands pressurized and safe. Within days, crews throw berms of regolith against the sunward side and over the roof, then add panels made from sintered soil. That cuts radiation and evens out temperature. Inside, a double wall liner creates a quiet thermal buffer. Warm air circulates between layers, so any cold corner or hot patch gets mixed away. Floors snap together like tiles, with built-in cable channels and anchor points for racks, because drilled holes in vacuum are not your friend. Air is a loop you fight to keep closed. Life support pulls carbon dioxide from cabin air, adds oxygen, and holds humidity where humans and electronics like it. Water is the lever. Condensed moisture from breath and sweat goes back into the tank. A compact system breaks down some CO2s and recovers oxygen. Tanks carry reserves for spikes and emergencies. Filters are easy to swap with gloves and placed waist-high, so no one has to kneel in a dusty suit layer to keep the base breathing. Sensors watch partial pressures and sound calm, unmissable alerts before numbers drift. Water is life and shield. A base that recycles well can reuse most of what the crew drinks, cooks, and washes with. Gray water runs through membranes and beds of media that catch fines and kill microbes. Clean water loops back to the tap and to cooling systems. Waste brine is minimal and stored for later processing. If local ice is available, small rigs heat soil and condense vapor into a clean stream, then store it in shield tanks that double as walls. No one promises a farm on day one. The first win is straightforward: a stable, ample supply for people, suits, and radiators. Power is the heartbeat. Near the South Pole, sunlight skims certain ridges for most of the month. Lightweight, Roll-out solar arrays rise on short masts there, connected by cables to the base below. The 2-week night is the real test. Batteries can carry you only so far. Regenerative fuel cells, which store solar energy by splitting water and then recombine hydrogen and oxygen to make power at night, bridge the gap without hauling tons of new fuel from Earth. Small fission systems add steadiness. A compact reactor runs quietly day and night, giving the base a floor of reliable power so the life support never plays roulette with the sun. Heat management is as important as volts. The habitat dumps waste heat through radiators that face cold space and hide from dust. When the sun moves low, the whole base can pivot on a small pad or deploy shades so radiators never see direct glare. Inside, a liquid loop moves heat from crowded racks and galley gear to the outside. At night, that loop can reverse, scavenging warmth from batteries and electronics to keep cabins comfortable without wasting power on heaters. Workflows beat heroics. The base is laid out with a dirty side and a clean side. Suits, drills, and sample boxes live on the dirty side near the airlock. A small workshop sits just inside, with a vacuum bench, a glove box, and racks of labeled parts, no rummaging. The clean side holds bunks, galley, medkit, and comms. Lanes are marked on the floor so a dusty tool never crosses into sleeping quarters by accident. End-of-day routines are short: purge, wipe, filter change if needed, log. In the morning, task boards light up with a plan that fits the day's power and radiation forecast. Mobility extends the base's reach. A pressurized rover plugs into the habitat like a room on wheels. Crews can work in shirt sleeves along a route, then don suits for short sorties and return to warmth fast. Unpressurized carts carry cargo along marked lanes. A small crane or telehandler does the heavy lifting. Solar pallets, sintering tiles, instrument masts. Robot helpers drive often moving rocks from paths, checking radiator cleanliness and pre-positioning supplies before a human EVA. Every kilometer driven by a robot is a kilometer of risk the crew does not take on foot. Food begins with stowage and grows into fresh. Early menus lean on packaged meals, balanced for long shelf life and low mass. A plant growth rack adds morale as much as vitamins. Greens under LED light, watered by reclaimed moisture, trimmed, and eaten the day they are ready. Crew psychology matters. A warm meal, a green leaf, and a clean window onto the landscape turn a tough job into a human place. Quiet hours are real. Exercise gear fits the room and the schedule because strong bones and calm minds are as critical as strong batteries. Waste is a resource waiting for a plan. Organics that cannot be recycled immediately are dried and stored safely. Packaging is sorted. Plastics become patches or feedstock for a small printer. Metals stack for return or later use. Dust collected by filters is a scientific record and a maintenance headache. It is sealed, labeled, and studied to refine cleaning routines and landing pad design. Nothing leaves the airlock unless it must. Nothing enters the cabin unless it must. Communications bind the outpost to Earth and to itself. A high-gain antenna talks to relay satellites and to gateway. A low-gain backup stands by. Surface beacons around the site broadcast precise timing and position so rovers and people can navigate without guessing. Internally, wireless links are short and robust, with wired backups for the racks that cannot go down. Cameras and mics in the workshop let experts on Earth stand next to a crew member during a delicate repair. But all procedures are written so the team can work if the signal goes quiet for an hour. Safety is layers, not luck. Fire hazards are few. Non-flammable materials, careful cable routing, and power limits on outlets. Medical kits are simple but thorough, with ultrasound, IV supplies, and a telemedicine playbook. An escape plan is always current. If a leak appears, which hatch seals, which pump isolates a loop, which rover becomes a lifeboat. Drills happen on calm days, so muscle memory is ready on hard days. The best base feels a bit boring. Boring means predictable. Predictable means safe. Growth is modular. A second habitat plugs into the first through a pressurized tunnel. A dedicated lab arrives and takes over the glovebox load. A larger solar field climbs the ridge, and a second power path feeds the grid. Adding pieces does not change the rules because the interfaces are standard. Every new module has the same air fittings, data ports, and docking collars. That is how a campsite becomes a town without rewriting the manual. Do this well and a lunar stay becomes a rhythm rather than a stunt. Power hums. Air is clean. Water flows in circles. Dust stays where it belongs. People work, sleep, and call home. They bring back cores, not just rocks, maps, not just photos, and a checklist of improvements that make the next rotation smoother. That is sustainable exploration in practice, a place built to last in a place that has not changed for billions of years. Lunar water ice is the quiet prize of Artemis. If we can reach it, measure it, and use even a little, the moon shifts from a campsite to a workshop. Water keeps people alive. Split into oxygen and hydrogen, it becomes air and propellant. Stored around habitats, it doubles as radiation shielding. One resource solves three problems at once. What do we know? Orbiters mapped clues in several ways. Neutron detectors found pockets of hydrogen just below the surface. Infrared spectrometers saw water and hydroxyl signatures that strengthen in darkness and ease in sunlight. Radar peered into shadow and returned reflections consistent with buried ice. A deliberate impact blasted debris from a polar crater and detected water in the plume. The result is a nuanced map. Some deposits are thin frost near the top. Others are grains mixed into soil. A few may be cleaner slabs tucked into permanently shadowed pockets. The target zones are permanent shadows. In some polar craters, the sun never reaches the floor. Temperatures plummet, and ice can survive for geologic time. These cold traps are promising and punishing. Terrain is steep and jagged. Rims bask in long sunlight, while pits stay black. Exploring them demands careful lighting, relay communications, and machines that work in deep cold without cracking seals or fogging optics. Prospecting comes first. You do not build a mine with a map alone. A rover brings three truths: where the hydrogen is, how strong the ground is, and how ice behaves when warmed. A neutron spectrometer sniffs hydrogen while rolling. A drill or pneumatic corer brings samples from several depths into a chilled path. An oven warms measured scoops and logs what boils off water, carbon dioxide, and other volatiles. A thermal probe measures how heat moves through the soil to reveal how tightly ice is bound. Together, these readings turn orbital hints into ground truth. The cold chain is essential. Warm a sample at the wrong moment, and you lose what you came to measure. Sample paths stay shaded and chilled from shovel to sensor. Seals and valves flex at cryogenic temperatures without tearing. Data rides up a relay mast on the rim, so radio links stay clear. Nothing is left to chance. A single broken thermometer can distort a map. Extraction starts small and simple. Thermal mining warms soil in place and captures the vapor. Heaters can be rods pushed into the ground or blankets draped like a low tent. A flexible skirt seals edges. Vacuum pumps pull vapor toward a chilled coil that sits in shade. The coil condenses water into a tank. Mechanical digging is the other path. Scoop soil, carry it to a warm box, bake, and dump dry tailings into a berm that later shields radiators and arrays. Both approaches hate leaks and clogged filters, so joints are simple and lines are short. Power sets the pace. Heating regolith is energy hungry, so early systems pulse work to match solar peaks. Arrays on bright ridges charge batteries by day and run heaters in bursts. Nights are bridged by fuel cells. A small fission unit, when available, turns stop and go into steady work. Either way, First-generation plants chase reliability before volume. Purity matters. Polar ice is not bottled water. It can carry sulfur compounds, organics, and dust. Early liters run through filters and simple distillation for drinking and for electrolyzers. Later, resin beds and membranes polish the product. The waste stream is logged and stored. Scientists want to know what else rose with the water because it records delivery from comets and the solar wind. Once you have water, storage is strategy. Tanks live in shade under berms or in shallow pits. Lines run to the habitat for drinking and cooling. An electrolyzer nearby splits water into oxygen and hydrogen for high-pressure tanks or cryogenic dewars. Oxygen is the heavy lifter. In most propellant mixes, oxygen dominates the mass. Even if hydrogen proves scarce or hard to store, making oxygen locally from ice or even from lunar rock slashes what must launch from Earth. Moving fluids on the moon is its own art. Exposed pipelines are fragile across rough ground. Early on, rovers with insulated cistern pods shuttle water or oxygen between the shade plant, the habitat, and a lander. Later, short, protected lines connect fixed points under berms with quick disconnects for maintenance. Operations protect science and safety. Cold traps are natural archives. Teams keep landers, exhaust plumes, and waste heat far from sensitive floors. Routes are set so wheels do not cut trenches. Work happens in planned campaigns. Map, sample, test, retreat, analyze, refine. Disturb as little as possible while learning to live there responsibly. What if the ice is patchy, dirty, or deeper than hoped? Then strategy adapts. Oxygen from regolith becomes the bridge. Free oxygen from minerals, while water for people rides on cargo flights at modest mass. If ice is abundant and accessible, investment shifts to power, pads, and storage. The choice is measured based on energy per liter, reliability, and crew time. Success is small before it is big. A win could be tens of liters per day into clean tanks, enough to cover life support margins and feed a fuel cell at night. Next comes a pilot plant that runs for a month without constant babysitting, proving heaters, pumps, and seals survive dust, cold, and thermal cycles. When those boxes check, scaling to propellant is real. If they do not, we still win. Limits become numbers, not guesses. The payoff reaches beyond the moon. Every valve, freezer, and drill proven in the shadows teaches us how to work on Mars and icy moons. The discipline of cold operations, clean handling, and careful accounting of power and mass is a universal skill for living off the land in space. If Artemis turns polar ice from mystery to managed resource, the line between mission and industry will blur. That is when the moon stops being a destination and becomes part of our neighborhood. Science gives Artemis its compass. Flags fade. Data lasts. Every landing that builds infrastructure also builds a laboratory, because the moon is not just a destination, it is a museum, a seismology station, a chemistry set, a biology lab, and a radio observatory rolled into one airless world. Begin with the ground's heartbeat, moonquakes. Apollo's few seismometers prove the moon shivers deep quakes from tidal flexing, shallow quakes that rattle like a passing truck, and steady pings from micrometeoroids. Artemis can scale that from a handful to a network. Lunchbox seismometers ride on cargo landers and rovers and ring the South Pole. Linked by relays to Gateway, they triangulate every thump. The result is a true interior map crust thickness, mantle structure, and even the size and state of the core. Seismology pairs with heat flow. Slender probes slide into the soil to watch how fast heat moves. That reveals how fluffy or compact the regolith is, how rocks conduct, and how much warmth the moon still leaks from its birth. Add surface magnetometers, and we trace patches of remnant magnetism frozen into ancient lava. Together, heat and magnetism show how small rocky worlds cool and why some regions remember long-vanished magnetic fields. Where those properties change abruptly, engineers mark, "Do not drill blindly." Geodesy precise shape and motion quietly powers everything else. Retroreflectors left by Apollo still bounce lasers from Earth, timing the moon's distance to millimeters and testing gravity itself. Artemis adds new reflectors at the poles and beacon towers around base sites. With them, landers tighten their target ellipses, rovers navigate like surveyors, and the whole community shares one high-precision map. When a boulder shifts or a landing pad settles, the network sees it. Chemistry is the long game. Cores pulled from layered deposits are calendars. Volcanic glass beads trap tiny bubbles that record volatiles, the water and carbon history of the lunar interior. Frost scraped from a cold trap tells how comets, asteroids, and the solar wind have delivered hydrogen and oxygen over eons. Every gram is logged, exact spot, depth, temperature, and handling chain. Back on Earth, labs read isotopes like fingerprints to trace origins. The payoffs reach beyond the moon. Those calibrations let us date surfaces across the solar system with confidence. Astronomy at the moon is a superpower of silence. The far side is radio quiet, the one place in the inner solar system shielded from Earth's chatter. Unroll a low-frequency antenna array across a dusty plain, and you can listen to the universe's dark ages before the first stars turned on. At the poles, stable, cold sites make infrared instruments efficient. No atmosphere, long nights, and firm mounts. Modest telescopes can do precise photometry, laser comms, tests, and tracking of near-Earth asteroids without atmospheric distortion. Biology moves from theory to experience. Low Earth orbit taught us microgravity. The moon offers partial gravity and deep space radiation the mixed crews will actually live in. Short, focused experiments ride with every crew. Bone and muscle response at 1/6 G. Sleep and cognition across long days and long nights. Skin microbiome shifts in a closed, dusty habitat. Wound healing when small cuts meet sharp regolith. And how diet, exercise, and light cues steady circadian rhythms when sunrise comes every 2 weeks. Plants get their turn. A compact rack grows hardy greens under LEDs, not just for salad. Roots report how partial gravity changes fluid flow and nutrient uptake. Leaves show whether low G reshapes growth hormones. Seeds flown to Gateway and to the surface come home for germination tests. Microbes and biofilms are studied because they will either be helpers, closing water loops and digesting waste, or troublemakers on filters and seals. Radiation biologists run shield versus dose comparisons in real time, building dose-response curves that guide shielding and schedules. Dust toxicity finally gets numbers. Tiny chambers pull measured amounts of authentic lunar dust through filters that mimic lungs, tracking inflammation and clearance. Surface crews wear smart masks in the lock on dusty days and skip them on cleaner days so physicians can compare outcomes. The aim is not fear, it is thresholds. How clean is clean enough? How long can someone work outside before eyes and airways complain? Answers become checklists that prevent chronic harm without choking productivity. Robotics multiplies science hours. Small, tough scouts handle the risky edges, peering into shadowed pockets, laying antenna tape, planting seismic nodes on slopes. Crews teach them during the mission. Later, the robots run the same routines without supervision. When people leave, the instruments keep working. Gateway stores months of data, relays commands, and lets Earthside teams continue experiments long after boots have gone home. Every instrument shares power, time, and downlink with life support. So discipline matters. Payloads earn their mass by being simple, modular, and repairable. If a sensor dies, a crew swaps a card, not a crate. Standard mounts and connectors let new experiments ride in on the next cargo lander and click into open slots. The base is a living lab, not a museum. Today's seismometer node can become tomorrow's weather mast or comms repeater. The payoff is layered. We read the moon's past to understand Earth's history and the birth of rocky planets. We test gear and habits we'll need for Mars. We set health baselines in partial gravity so future crews don't guess at risk. And we prove that a station and a base can host real science without pausing operations. Exploration becomes a rhythm. Arrive, build, measure, learn, upgrade, and leave the place better equipped for the next visit. Science is the part that keeps paying back years after a mission lands. With Artemis, the moon stops being a single story told in a week and becomes a bookshelf, each mission a new, well-labeled volume that the next team opens and continues. Private industry is the accelerator of Artemis. Government sets the destination and the safety rules. Companies turn designs into hardware that flies often, gets cheaper, and improves with every mission. That blend is the difference between a single headline and a transportation system you can schedule. Start with the human landing systems. NASA is not buying a single fixed vehicle. It is buying a service. Carry 2 astronauts from lunar orbit to the surface and back under strict safety gates. Providers compete on how to do it. One path is a very large, single-piece lander refueled in space with a roomy cabin and an elevator to the ground. Another is a 2-stage design with a stout descent stage and a lighter ascent cabin. Both aim for reusability, and both rely on cryogenic propellants that must be stored and transferred in space without boiling away. Refueling is the hardest new trick. Supercold oxygen and either methane or hydrogen will flash to gas if a tank warms even slightly. Commercial teams counter with sun shades, multi-layer insulation, radiators that stare into deep space, and active zero boil-off systems that hold temperatures steady during long loiters. Docking rings, hoses, and valves follow common standards, so a tanker from one company can top off a lander from another without a custom adapter. That is how you scale beyond prototypes. 2 marquee providers sharpen each other. SpaceX pursues the giant path, a tall, refuelable lander with deep throttle engines that can hover gently and then push hard to climb. It depends on multiple tanker flights and clean cryogenic transfer in Earth orbit, trading early complexity for a high-capacity vehicle later. Blue Origin leads a modular family that burns hydrogen and oxygen and separates descent from ascent, with partner companies supplying avionics, guidance, and mission software. Competition makes both better. If one pauses for upgrades, the other can keep the cadence going, and the program avoids a single point of failure. Cargo keeps the drumbeat between crew flights. The Commercial Lunar Payload Services program buys quick, relatively low-cost deliveries on small landers. Some succeed, some fail. All teach a short landing that drops a drill, a weather mast, or a reflector and reports honestly about dust, thermal swings, and communications moves the whole architecture forward more than a perfect simulator run. Companies that touch down near target stay healthy through the lunar day and talk to the network, earn repeat work, and pull the schedule to the left. Launch is a mixed fleet. Heavy, crew-rated rockets lift Orion. Commercial heavy lift boosters throw cargo and components toward the moon on their own cadence. That decouples people from freight. If a cargo rocket slips a week, a crew does not sit on the pad. A later refueling window picks up the slack. Markets reward that flexibility. A firm that can fly monthly earns business that a firm stuck on a yearly tempo will miss. The business model matters as much as the metal. Fixed price, milestone contracts pay only when a provider proves a step is real. Engine tests passed, docking demo complete, guidance software running on flight hardware. The incentive is to move fast, iterate, and solve problems permanently, not to write longer reports. At the same time, NASA's technical authority draws non-negotiable lines around crew safety, redundancy, fault tolerance, abort modes, materials, software standards, and test depth. Speed lives next to rigor. Neither works without the other. Open standards glue the ecosystem. Docking rings, power plugs, data links, timekeeping, and navigation follow published specs. That lets a new lander talk to Gateway without an expensive adapter, or a rover plug into a habitat without rewiring. It also enables a cislunar internet relay satellites, ranging beacons, and laser links that any vehicle can use, so navigation and communications become shared services instead of bespoke projects. The more common the interfaces, the faster the market compounds. Risk is managed by cadence and diversity. Artemis does not bet everything on one lander, one launcher, or one vendor. 2 human landing systems run on parallel tracks. Multiple cargo providers compete for CLPS missions. Several launch vehicles move pieces on different schedules. A failure is a lesson, not a cliff. The goal is not to make risk vanish. It is to make risk survivable by never letting a single delay halt the chain. Culture may be the biggest shift. Commercial teams test in public, fail fast, and fly again. Government teams publish, peer review, and certify. Put together, the program both learns quickly and locks in quality. A flight that scorches a panel or tips a small lander on uneven ground is not a scandal. It is data that shapes the next design of pads, legs, or autonomy. The winners are the companies that adapt visibly shortening hoses, moving sensors higher, tuning software to see rocks in low sun, and proving in hardware that the lessons stuck. Partnership reaches past the lander. One company might field a pressurized rover, another deploys a power kit on a sunlit ridge, a third runs a communications relay, a fourth delivers drills and sample chains. International partners fly habitat pieces, robotic arms, and life support upgrades that click into the same ports. Universities deliver instruments in shoebox form factors that bolt to standard pallets. Even medical monitoring and telesurgery tools ride in as commercial gear that must work in rough hands and dusty corners. Economics follow capability. A lander that flies twice a year creates steady demand for tankers, navigation beacons, and cargo tugs. A base that sips local water and oxygen spawns contracts for heaters, drills, and cryogenic tanks. A network that beams timing and maps across the South Pole sells subscriptions to every rover and lander that needs a fix. None of this is science fiction. It is the same pattern that followed the first weather satellites and Jeep. Once a service works, it becomes invisible and indispensable. Transparency keeps the neighborhood safe. Providers publish planned trajectories and frequencies, share landing coordinates and schedules, and respect keep-out zones around heritage and sensitive science sites. If 2 missions want the same ridge, a schedule and standard separation keep the peace. If a lander suffers a fault, others are ready to help under agreed rescue and assistance norms. These rules are boring in the best way. They keep drama on the engineering bench, not on the surface. The payoff of this public-private model is compounding improvement. The first reusable lander is expensive and finicky. The 5th is cheaper, cleaner, and easier to turn around. The first drilling rig clogs on day 3. The 3rd runs for a month. The first refueling takes all night. The 10th finishes before dinner. With each step, the moon gets closer to feeling like a place where work sticks. Artemis is the scaffolding. Industry is the crew on the planks. Together, they are building something we have never had before: routine access to another world. When companies can count on flights and customers can count on schedules, a frontier turns into an economy, and the moon shifts from a story about the past to a platform for everything that comes next. The new moon race is not a sprint, it is a standards race. Countries and companies are aiming for the same sunlit ridges and the same shadowed craters, but the decisive contest is about behavior, what rules we follow when rockets, robots, and people share one small world. The United States leads with Artemis, a partnership of national agencies, private industry, and a growing circle of nations aligned on common principles. Those principles sound simple: be transparent, share positions, help in emergencies, protect heritage sites, avoid harmful interference, but they become daily habits. Publish landing coordinates early so two missions don't aim for the same patch of ground. Keep radios and laser links within agreed bands so science instruments aren't drowned out. Use dust-safe approach corridors. Treat rescue and assistance as a duty, not a favor. China leads a parallel path. Its plan for a long-term presence, branded as the International Lunar Research Station, envisions a base in the 2030s with power, communications, and shared labs built step by step. In practice, that means robotic scouts, precision landings, and technology demos that advance outward year by year. Where Artemis emphasizes widely published norms and open interfaces among many partners, the ILRS model emphasizes a cohesive alliance that builds a shared outpost over time. Both approaches seek safety and cadence. They differ in how they organize trust. Other nations are not bystanders. Europe provides propulsion, life support, navigation tech, and key pieces for the small station in lunar orbit. Japan is building logistics systems, life support upgrades, and a pressurized rover that can carry crews far from camp and keep them warm through the long cold. Canada's next-generation robotic arms will work the edges, catching vehicles, moving experiments, and inspecting arrays. India, with a polar landing and extensive orbital mapping, has shown that careful, steady progress can unlock hard targets. South Korea, the UAE, Australia, and others are adding instruments, tracking, and operations know-how. The map is getting crowded in the best possible way. Competition is obvious, but cooperation is the grease that keeps gears from grinding. Even rivals share space weather data because a solar storm doesn't pick sides. Tracking networks trade warnings when debris or a drifting booster might cross a trajectory. Laser retroreflectors and surface beacons help any lander refine its aim. The radio-quiet far side is a special case. Astronomers want it treated like a park, with strict limits on transmitters so low. Frequency cosmic dawn experiments can listen without Earth's chatter. That shared silence is one of the few places where everyone benefits by holding back. Why do norms matter so much? Because lunar geography squeezes us. The best South Pole sites are narrow ridgelines with long sunlight and nearby access to permanently shadowed cold traps. There are not many of them. If two missions crowd a ridge, exhaust plumes and dust can sandblast panels and instruments. If a lander touches down in the wrong spot, it can block a route a rover needs to reach a science target. Deconfliction is not paperwork. It is protection for hardware that must survive months of cold, heat, and grit. Two legal layers shape behavior. The foundational Outer Space Treaty bans sovereignty claims and demands due regard for others. Newer, voluntary principles adopted by many nations translate that phrase into practice. Register missions, share maps, mark temporary safety zones during active work, and plan for debris and end-of-life disposal. Teams aligned under ILRS publish their own roadmaps and memoranda. The documents differ in tone, but crews still face the same daily chores: land gently, keep dust under control, mind your neighbors, and leave the place safer than you found it. Think of 3 kinds of friction good rules prevent. First, spectrum fights. The moon will host navigation beacons, relay satellites, science, radios, and lander links, so clear coordination keeps loud transmitters from drowning out faint instruments. Second, dust fights. Plume, safe pads, separation distances, and agreed approach corridors keep one landing from sandblasting another's arrays. Third, traffic fights. A shared registry of planned routes and parked hardware keeps rovers from driving blindly into someone else's test range. There is also a race on cadence. The side that flies more often learns faster. Frequent cargo landings, map hazards, measure radiation, and test pads and coatings in the real environment. Crewed flights then inherit better procedures and sturdier parts. That is why commercial providers matter. They can take smaller risks on quicker schedules while national crews fly a measured tempo. When both tempos inform each other, progress compounds. Money and public patience decide who keeps going. Programs that turn early wins into visible services, reliable navigation beacons, fast relays, precise maps. Sample labs that publish earn support that survives a delay or a headline failure. Programs that overpromise dates and underdeliver capabilities invite cuts. The sober way to win is to make the moon boring in the right ways. Regular truck runs, predictable communications, dependable power, and no surprises when a crew shows up tired and on the clock. Security questions sit at the edges. Space is dual use by nature. The same tracking network that helps a lander navigate can also watch military objects. The same precision landing tech that touches down near a fragile crater could, in principle, place anything with unsettling accuracy. The answer is not panic. It is transparency. Publish interfaces, publish schedules, keep lines open at the working level, and treat aid to crew as non-negotiable. When something breaks, the nearest safe harbor should always be, "Come here," regardless of the logo on the suit. Who steps on the moon first in this era matters less than the habits we establish. If the first landings are cautious, dust-aware, and honest about lessons learned, then the second, third, and 10th will inherit less risk. If early missions bulldoze ahead without sharing, everyone pays later in broken gear, stricter rules, and harder politics. The moon is a small town. Reputations travel fast. The optimistic view is hard-earned but real. We already see shared maps with centimeter detail, joint field trials, and quick-look science releases. Astronauts train together. Engineers swap test data on valves, seals, and software glitches. Universities on several continents build the same shoebox instruments to the same bolt patterns so they can ride whichever lander has room. These are not big headlines. They are the threads of a durable fabric. In the end, the next space race will be won by whoever makes the moon safe and useful for everyone by the team that lands gently, shares honestly, and leaves the place better than they found it. Flags will matter less than flight plans. The reward is a stable cislunar neighborhood, a clear road to Mars, and a generation that sees the moon not as a trophy, but as part of home. Mars is why back to the moon matters. The moon is close enough to practice, far enough to be real. Mars is far enough to punish every mistake. Artemis is the training ground where hardware, routines, and people learn what long interplanetary missions actually demand and what they refuse to forgive. Time comes first. A lunar mission lasts days to weeks. A Mars mission lasts years. Transit alone takes many months. There is no quick rescue. That pushes every system toward margin, durability, and repairability. On the moon, we learn which pumps clog, which valves stick, and which software recovers from faults without a reboot. We learn what crews actually use, how to swap parts in gloves, and how to keep spares clean in dust. Those habits travel. Radiation shifts from concern to constant. Lunar crews step outside Earth's shield and duck back in. Mars crews live under cosmic rays the whole trip. Storm shelters, water walls, and hydrogen-rich liners tested around the moon become standard structure for deep space habitats. Personal dosimeters and cabin sensors, plus conservative work-rest rules, must feel normal. Artemis turns radiation from theory into muscle memory. Gravity is the next rehearsal. Microgravity weakens bone and muscle. 1/6 G. On the moon is a partial dose. Mars gives 1/3. We still do not know the long-term health breakpoints. Long lunar stays with smart exercise, diet, and sleep across harsh light cycles provide the missing middle. If crews keep bone density, balance, and dexterity healthy at lunar G, we can tune countermeasures and workloads for Mars. Life support needs closure. On the Moon, water and air loops can be corrected with modest cargo. On Mars, resupply is a slow boat. Artemis pushes recycling further. Filters that last months, CO2 scrubbers that regenerate many times, biofilms that behave, and plumbing that tolerates grit. Every percentage point of recovery proven on the Moon means less mass launched for Mars. Power is a split problem. Lunar South Pole sites enjoy long sunlight but still face cold nights. Mars has sunlight too, but dust storms can dim it for weeks. The fix is diversity. Artemis hardens solar arrays, radiators, and power beaming across ridges. It also matures compact fission that ignores weather. The goal is not a single best source. It is a mix that survives failure, the same mix that will ride to Mars. Dust is different and the same. Lunar regolith is sharp, glassy grit. Martian dust is reactive and may carry perchlorates that irritate skin and lungs. The discipline is shared: dirty lock, clean lock habits, electrodynamic dust removal, suitports, and smooth, easy to clean hardware. Artemis drills the choreography until it is boring. Mars will thank us. Landing is where the planets diverge. The Moon has no air. Mars has enough to cook a heat shield on entry, and not enough to land with parachutes alone. Supersonic retropropulsion, the art of firing engines into high-speed flow, will decide Mars' missions. Guidance, throttling, and plume control perfected over boulder fields at the lunar South Pole carry into thin air descents. Terrain relative navigation, hazard maps, and divert logic learned at the Moon become the difference between a safe pad and a crater. ISRU, using what is there, links the worlds. On the Moon, we chase water ice for drinking, oxygen, and maybe propellant. On Mars, we can pull CO2s from the air and oxygen from the soil. With hydrogen brought or found, methane becomes fuel. Stubborn pilot plants at the Moon teach patience with heaters, seals, cryotanks, and valves that must work for months without babysitting. That patience is the culture Mars requires. Communications delay forces autonomy. A round-trip radio lag to the Moon is seconds. To Mars, it is many minutes. Artemis leans into supervised autonomy. Vehicles that fly and land themselves while people set goals and intervene only on big decisions. Crews learn to be their own mission control, triaging checklists, pacing workload, and solving surprises with what is on hand. Independence is survival. Psychology is mission critical. The Moon lets us study sleep across 2-week days and nights, mood under isolation with a view of Earth, and teamwork when fatigue meets risk. Quiet routines, windows with a horizon, private space, and bite-size, meaningful science tasks matter. On Mars, the view is lonelier and delay makes conversations asynchronous. Artemis helps build the mental toolbox: journaling, self-briefs, conflict checks, and rituals that mark time. Logistics is the quiet wall. A Mars stack includes a deep space transport, an entry vehicle, a lander, a surface habitat, rovers, and ascent hardware pre-positioned and verified before crew departure. Artemis practices the choreography: gateway as a staging port, tankers topping up landers, cargo pre-delivered to precise sites, and standard ports and plugs that let pieces mix and match. If you cannot do it at the Moon with minutes of delay and simple aborts, you cannot do it at Mars with months of delay and no rescue. Science pays forward. Seismic networks, heat flow probes, dust and radiation logs, and resource maps built on the Moon refine the models used to pick safe Martian landing zones and drill sites. Biomedical data from partial gravity guides, rules for EVA length, sleep, and recovery. Even the boring stuff labels, sample chains, and dust-proof packaging translates directly to a planet where resupply is a year away. Finally, culture. Iteration over heroics. The first attempts will be imperfect. The win is cadence fly, learn, upgrade, repeat without resetting the calendar after a setback. Artemis must prove we can absorb failure, publish lessons, and return stronger. That is the only culture that survives a frontier. In short, Artemis is not a detour on the road to Mars. It is the roadwork grading, drainage, signs, and practice runs. When a crew steps onto the red plains and looks back at a lander that will still be there when they return, the quiet confidence underneath will be 1,000 small habits learned in lunar dust. When to pause for space weather, how to land near rocks without touching one, and how to end a long day with a base that hums like home.